Hi, this is Colleen, and I will be teaching you about how to use integrals to find displacement of particles.
Hi, I'm Ari, and I will be teaching you about how to take the derivative of a function that includes both sine and cosine.
We hope you enjoy the show. Oh, hey there! Didn't see you there. Would you like to learn about some math? Okay, let's get to it.
First, we will talk about sine and cosine. Sine and cosine are the basic functions encountered in trigonometry. Sine is a function of an angle. In a right triangle, sine gives the ratio of the length of the side opposite to an angle to the length of the hypotenuse. In a right triangle, cosine gives the ratio of the side adjacent to the angle to the length of the hypotenuse, as you see here. Good. More specifically, we're going to talk about the derivatives of sine and cosine. The derivatives of trigonometric functions are the rate at which the function changes with respect to a variable. The derivative, and this is the derivative of a trigonometric function. First, we're going to start by solving a basic problem involving sine and cosine. The function that we will be taking the derivative of is sine squared x plus x cubed minus x to the fourth plus cosine 4x. Okay. To start by taking the derivative, you need to know the derivative of sine. The derivative of sine is cosine, which you should have already learned by now, and the derivative of cosine is negative sine. Okay, so we have to apply the chain rule here, and to do that, you move the exponent in front of the equation, and then you take you multiply it by the derivative of the inside, and then we take the derivative of x to the fourth, put the 4 down, and you minus 1, so minus 4x to the third, plus, put the 4 front, 4 cosine, and I forgot that one. So, because I forgot it, we're just going to sneak it in here. And the derivative of x to the third is...
Sorry guys, people make mistakes. That happens sometimes in math. So let's continue.
Okay, so to continue, we know how to take the derivative using the chain rule of sine squared x plus 3x squared, the derivative of x cubed, minus 4x cubed, and then we will use the chain rule to take the derivative of cosine 4x, which would be, bring it down here, 4 cosine x times negative sine x. So we have our final product, just to simplify it, would be 2 sine x cosine x plus 3x squared minus 4x cubed plus, it's going to be a minus because the sign is negative, so put the negative in front, negative 4 cosine x sine x, and that is your final product. Hey guys, we're going to be moving on to a difficult problem now. Hopefully the basic problem wasn't too hard for you because it was pretty basic. Alright, the function that we will be taking the derivative of is y equals 1 minus cosine x over sine x. To solve this problem, we're going to need to know what the quotient rule is. The quotient rule is you take the derivative of the first function times the derivative of the second function minus first function times the derivative of the second function over the second function squared. This is f and this is g. Okay, to take the derivative, we multiply it by sine x, which is the derivative, sine x, which is the derivative of negative cosine x, times sine x, the bottom, minus the first function, 1 minus cosine x, times the derivative of the bottom function, and the derivative of sine is cosine x, all over sine x squared. Okay. Now to simplify the derivative, sine squared x plus cosine squared x minus cosine x over sine squared x. Hopefully everyone sees how I got that. I had to distribute the negatives and I ended up with this. Okay, and to simplify this further, you need to know that sine squared x plus cosine squared x equals 1. Therefore, we can simplify this to be 1 minus cosine x over sine squared x. Hopefully you all got that. Okay guys, now it's your turn. Here is an extended problem for you to try. And I suggest leaving out this one part. So you'll need to determine the rate of change of theta when t equals 3 seconds, which should not be too difficult for you, so good luck!
Hey y'all, I'm back again. It's me, Grendel, or Grenfell, as you may know me. Anyways, we're going to be moving on to our next topic now, using integrals to find displacement of particles. Yay! In taking the derivative of a function, the antiderivative of an integral is equal to this. When n does not equal 1. So, to take the antiderivative, you add 1 to the power, then divide the coefficient by this new power, and then add c. For example, 2x squared d to the x would turn into 2 over 2 plus 1 x raised to the power of 2 plus 1, which equals 2/3 x to the third plus c. You can use integrals and antiderivatives to find displacement of particles. It is important to note that this technique does not reflect the total distance traveled, it reflects the difference in distance between 2 points. This is because when using integrals to find displacement, going to the right will give a positive number, and going to the left will give a negative number. Because you take that number, not its absolute value, the displacement could end up being 0 or even negative. To use integrals to find particle displacement, you need to take the antiderivative of a velocity function. So, if a particle is moving at a velocity of v of t equals 2t squared plus 3t cubed plus 4t, find its displacement. This solves, using the rules we discussed, to p of t is equal to 2/3 t to the third plus 3/4 t raised to the fourth power plus 2t. Yeah. Now that we've mastered the basic problem, let's move on to the advanced problem. Find the displacement from t equals 0 to t equals 2 of a particle with a velocity of 1/2 t raised to the third minus 1/4 t squared plus t. However, it's important that you must take it from 0 to 2 seconds. So, plugging in these numbers, you get and this all turns out to be 0. Therefore, your answer is equal to 10/3. Now here's an extended problem for you to try. Find the total displacement of a particle from 0 to 6 seconds. Remember that position is the antiderivative of velocity, and therefore the area under the curve is equal to the displacement. Good luck!